For those who've suffered a traumatic spinal cord injury and are paralyzed, there's rarely encouraging news, which is why what's happening in early clinical trials in a research lab in Lausanne, Switzerland, is so remarkable. A renowned French neuroscientist, Grégoire Courtine, and Swiss neurosurgeon, Dr. Jocelyne Bloch, have implanted a small stimulation device on the spine of paralyzed patients, helping them once again stand up and walk. What's even more surprising is their newest innovation, which uses an implant in the skull that enables patients to move their paralyzed legs or arms just by thinking about it. When we visited their lab, Neuro Restore, in March, they were working with a 39-year-old woman whose spinal cord was severed 6.5 years ago. She'd been told she'd never walk again.
Okay. You can roll to my side.
Marta Carstiano-Dombi is the most severely paralyzed patient who's enrolled in this clinical trial at Neuro Restore to regain mobility in her legs.
Try to go backward.
She has no feeling below her waist and isn't able to keep her balance. Just sitting up on her own is a challenge.
You catch me, huh? Sure. Good.
In 2018, Marta was a new mom, working at a German tech company when she began training with her husband for an Ironman competition. She was in the best shape of her life, but during the bike portion of the race, she suffered a devastating accident. You were found
near a tree.
Near a tree.
Yes.
And your back hit the tree.
We're hypothesizing what happened, right? Because nobody saw me. So I must have had a pretty tough collision because my spine basically broke like 2 dimensions.
Her spinal cord injury was so severe, doctors said there was no sign of nerve connections left to her lower body. She'd also broken 8 ribs, punctured her lungs, and was bleeding internally. She needed emergency surgery, and doctors told her family she might not survive. You came out of the surgery. I understand you wrote a message to your mom.
So the surgery took about 7 to 8 hours. And I was intubated. I could not talk. And my mom, you can imagine, she was in tears. And I just wrote to her, "I'm strong."
That strength has been tested. Marta spent 10 days in intensive care and 4.5 months in a rehab hospital, learning to adapt to her new life in a wheelchair. Traditionally, if someone gets a spinal cord injury, what are the treatment options for them?
You have to do a little bit of physiotherapy, get into a wheelchair, and then you go back home, and that's all.
That's it?
That's it. And that was, for many years, the only option.
Dr. Jocelyne Bloch and Grégoire Courtine have been at the forefront of researchers trying to expand those options since 2012. Their lab near Lake Geneva is a collaboration between the Swiss Federal Institute of Technology, Switzerland's MIT, and the Lausanne University Hospital. That's where they've implanted 8 paralyzed patients with a device that allows them to stimulate their spinal cords, enabling them to stand, take steps with a walker, and lift weights. Some can even climb stairs. They use a button to activate the stimulation.
Left.
And now, thanks to Courtine and Bloch's latest technology, 5 other patients can move their paralyzed limbs using their own thoughts. It's called a digital bridge, and it wirelessly connects a patient's brain to their spinal cord stimulator.
Normally, there is a direct communication between the brain and the spinal cord.
For me to walk, my brain just automatically tells my legs to walk.
Mm-hmm. But because of the spinal cord injury, the signal is interrupted. So we are aiming to bypass the injury by having a direct digital connection between the brain and the region of the spinal cord that control leg movement.
To do that, Dr. Bloch implants a small titanium device originally developed by a French research institute in the patient's skull, directly over their motor cortex, the area of the brain responsible for controlling movement.
You see, you have the 64 electrodes.
And so each of these is what?
It's electrodes that are recording populations of neurons underneath. And you can immediately see which one are the best correlated to a certain movement.
Mm-hmm. Like the hip is here, and then the knee is here, and then the ankle is here, etc.
Yeah.
Mm-hmm.
When a patient thinks about moving a limb, those electrodes record the brain's activity. Then a computer uses artificial intelligence to translate the recordings into instructions for the stimulation device implanted on the spinal cord. That device sends electrical pulses, activating muscles in the legs or arms. All of it happens in about half a second. Gert-Jan Oskam was the first person to get the digital bridge 4 years ago after he was paralyzed in a bike accident. We met him for a walk by Lake Geneva. So now the stimulation is on.
Now it's on, yes.
Do you feel it at all in your body?
I do feel a little tingling sensation from the stimulation with my brain.
His headpiece powers the implant in his skull, and on his walker is the computer. It's cumbersome and tiring, physically and mentally, but he can walk up to 450 feet. It's incredible to me, though, that you can continue talking with me even though this machine is reading the signals from your brain.
It's able to discriminate walking and talking at the same time. That's incredible.
For somebody who has not been able to control their movements, to suddenly be able to control their movement, I mean, that's...
Yeah, there is this initial phase of surprise, you know, when they realize that they are giving the order and it's happening, you know.
Nice. Wow.
That was me?
They're like, did I do that? Like, is it me or you actually stimulated, no? Say, no, you did it.
They think you're pressing a button somewhere and doing it.
They don't understand because I've been paralyzed for so many years.
Ready? Started. Increasing amplitude.
Marta got the digital bridge implanted in September. She's worked with a team of engineers and physical therapists to figure out how much electrical stimulation is needed to move her legs.
Nice.
Yeah.
And hop.
So that's the stimulation, the electrical stimulation is making the leg move.
Yeah, Marta is
starting to
completely
walk.
paralyzed.
This is the magic cappy.
But Marta's also had to teach herself to think about moving the exact same way every time,
Right?
so the AI can recognize her thoughts.
Left.
She practiced at first with this avatar.
Stop.
You have to relearn or rethink how to walk.
Exactly. So we were experimenting a little bit. What do I think about? Is it I think about the hip being contracted? Do I think about the knee lifting up? Do I think about the ankle?
To show us how she does that, they disconnected her skull implant from her spinal cord stimulator and connected it to this exoskeleton. You can control this with your thoughts right now.
Yeah, if I want to do a right movement, right hip flexion, it does a right hip flexion.
You're not pressing any
No.
buttons or anything, you're just thinking,
Sure.
can you look at me without looking at it and just
Do a right one,
Yeah.
yes. I think it works.
Yeah,
It does work.
work. After training with the digital bridge for just 2 days, Dr. Jocelyne Bloch and Gregoire Courtine, or G as Marta calls him, put her to the test, eager to see if she could take some steps.
Jocelyn and G come in and it's like, okay, show off. So what can you do?
They said show off?
Yeah.
Were you ready to show off?
I did not know if I'm able to show off. This was the thing, huh?
Using a harness to support about half her body weight and physical therapists to help place her feet on the ground, Marta took her first steps. Despite having no sensation below her waist, she was able to move her paralyzed legs with her thoughts. What was that like?
Gaining some superpower, a power that I did not have before. And now with these implants, you know, I'm a real iron woman. Nice.
When we were there in March, Marta wasn't able to walk on her own yet, but she said she'd already regained something she'd lost.
It's giving me my perspective back, standing up again and looking people in the eye. That's different.
A difference in how you think about yourself or in how others see you? Or
Both.
how you interact in the world?
Everything. Everything.
You leave the hospital on your wheelchair and you notice the different looks.
Right away, you noticed.
Yeah, scared looks. Also, a lot of smiles that are a little bit too long.
Those well-meaning smiles reminded Arnaud Robert, who's quadriplegic, how much his life had changed. A Swiss journalist, he'd spent decades traveling the world, but 3 years ago he slipped on a patch of ice and was instantly paralyzed from the neck down. He regained some function in his right arm with physical therapy, but wanted to see if the digital bridge could help him with his left. Opening and closing a hand is far more complex than walking.
It is because of the possibility to access a different muscle individually.
The hand is tricky with all these different little muscles, and it's very subtle.
But after surgery and training at Courtine and Bloch's lab for 8 months, he was able to use his left hand to help hold a glass and type.
Even to be able to move my fingers, this is something that I couldn't do. And of course, moving the arm like that, this is something that I couldn't do either.
That's incredible.
It's really incredible. I mean, I don't want to pretend that I'm using this left arm on a daily basis. There is a long, long way to get it functional for every quadriplegic in the world. But it was certainly a success because I see that I can do things that I was not able to do before.
But something else has happened as well. After using the digital bridge over time, both Arnaud and Gert-Jan have improved their ability to move their paralyzed limbs even when the system is turned off. How is that possible? What happened?
That was also our questions, and we could not do much in a human being to understand it.
Since it wasn't possible for them to see the changes in their patient's spinal cords at a microscopic level, they did studies in animals to understand what was happening.
What we understood was completely unexpected, that this training enabled the growth of new nerve connection. So new nerves start growing, and they grow on one very specific type of neuron that is uniquely equipped to repair the central nervous system.
So we also observed that the less the severity of the spinal cord lesion is, the better the regrowth happens. You know? If it's a complete spinal cord injury, it will be hard to regrow. But indeed, there is something happening.
How well the digital bridge works still needs to be studied in a lot more patients.
Go.
They hope to launch clinical trials in the U.S. in the next 2 to 3 years. The FDA has already designated it as a breakthrough device, which will prioritize the review process. And Courtine and Bloch have co-founded a company called Onward Medical to bring this technology out of the lab, making it faster, smaller, and widely available.
It's not changing my everyday in ways people might think, oh, she's getting back her life she had before. So as long as it makes me feel good, that I can stand up and hug my husband or hug somebody that I love, that means a lot.
What's your goal?
To go out in the park and just stand up and do some steps with my family. It's not a stroll in the park, how it would look for most other people, but for me, it's just good enough to make me happy.
After 6 months of hard work, just before Marta was to return to her family, she did what doctors years ago told her she never would.
Oh my God.
She took a few steps. No harness to hold her, just her walker and her iron will.
We don't often think about how the sense of touch makes our lives possible. We grip a paper coffee cup with perfect force to hold it, but not crush it. Our feet always find the floor. But for people with artificial limbs or those with spinal injuries, the loss of touch can put the world beyond their grasp. 17 years ago, the Defense Department launched a $100 million project to revolutionize prosthetic limbs. The robotics you're about to see is amazing, but as we first reported earlier this year, even more remarkable is how the feeling of feeling is returning to people like Brandon Prestwood.
For me, it was a battle if I wanted to live or die.
You weren't sure you wanted to live?
No. I didn't know if I wanted to or not.
Brandon Prestwood's battle began with the loss of his left hand. In 2012, he was on a maintenance crew reassembling an industrial conveyor belt when someone turned it on.
My arm was dragged in pretty much up to the shoulder. It crushed my bones in my arm and fed my arm through a gap about 1 inch.
How did they save your life?
The other maintenance guys jumped in. They started basically taking the machine back apart. Once we got it back apart, I could look in and see what was there, and one of the gentlemen was a Vietnam veteran.
And the Vietnam veteran knew what to do.
Yeah.
The Vietnam veteran knew tourniquets, but Prestwood lost his hand and couldn't return to his job.
Go eat this.
Yeah, that sounds good.
After 4 years with a hook, he told his wife Amy he wanted to volunteer for experimental research involving surgery at the VA.
I was not 100% on board to start with, but I knew he had his mind set that he had to do this, and I couldn't hold him back.
6 years later, thanks to Defense Department and VA projects, Prestwood controls this hand with nothing but his thoughts.
Everything still feel good?
Probably when I get her turned around here.
Electrodes implanted in muscles in his arm pick up his brain's electrical signals for movement. A computer translates those signals to the hand.
How about the middle finger now?
Sensors in the plastic fingers are connected to nerves in his arm to return a basic sense of touch,
Close your eyes, tell me when you're feeling each of these.
which he can demonstrate with his eyes closed.
Pinky. Index.
That's not bad.
Middle.
Still requires a little bit, but it's not bad.
Biomedical engineer Dustin Tyler leads this research at Case Western Reserve University and the Cleveland VA.
Touch is about connection. It's connection to the world, it's about connection to others, and it's connection to yourself, right? I mean, we never experience not having touch. It's the largest sensory organ on our body. All right, so go ahead.
Tyler first attempted an artificial connection in 2012. He switched it on in a volunteer and wondered what would happen.
So I was concerned, would it be his whole hand? Would it be painful? Would it not feel anything? We had no idea. So one of those big moments in my career was he came in, we first turned on the stimulus, and he kind of stopped for a second, and he goes, "That's my thumb. That's the tip of my thumb."
This happened right away.
First
It
time.
didn't require any training of the brain.
No, that was the beauty of it. My thumb.
Brandon Presswood remembers the instant it happened to him.
That's my fingers. I'm feeling my fingers that I don't have anymore. I'm feeling them.
A definite feeling, he told us, but different.
It doesn't feel exactly like my right hand. It's a tingling sensation. It's not painful. It's kind of like if your hand's been to sleep, right at the end, right before it wakes up, for me, it's pleasant. It's a pleasant tingling.
Let's see if you can do it in cherry here.
A tingling that's light with a light touch, but grows stronger the harder he presses. Eyes closed, he can pinch a cherry firmly enough to pull it from its stem, but not crush it.
You can feel this is light.
I had to use my lightest touch So if I hold this right here with an empty eggshell.
I can feel that. I feel it here and here.
It's a feeling more than a decade in the making.
At the beginning of this research, how did you even imagine that this would be possible?
I didn't imagine. I imagined that it was not going to be possible.
Sliman Benzmaya at the University of Chicago is among the world's leading experts on the neuroscience of touch. In 2008, he joined the Defense Department's project to revolutionize prosthetics, but he didn't think the Pentagon knew what it was up against.
There are 100 billion neurons in the brain interconnected with 100 trillion synapses. I mean, the human brain is like the most complex system in the known universe.
Too complex, he believed, to target electrical stimulation to exactly the right neurons.
And when we electrically stimulate, we activate hundreds, thousands of them at the same time in ways that would never happen naturally. It just seemed like that very impoverished interface with this nervous system would never be able to do anything useful. And turns out I was wrong.
He was proved wrong by his own research
How you doing, Scott? Nice to meet you.
Nice to meet you, Scott.
with volunteers including Scott Embry,
And you can feel that.
I feel it on my fingertips.
whose movement and sense of touch are limited by a spinal injury from a car accident. Computer ports in Embry's skull are wired to the motor and sensory parts of his brain. Electrodes pick up the brain's electrical signals that were intended for the muscles. A computer translates those signals to the robot arm. We first saw this brain-machine interface 10 years ago at the University of Pittsburgh, but back then there was no sensation.
Index finger?
In collaboration with Pitt, neuroscientist Sliman Bensmaya showed that signals for touch could be returned to the brain.
How can you possibly know what part of the brain is the tip of the index finger?
We took Scott and we put him in a functional magnetic resonance imaging scanner. And then we had him imagine moving his thumb, imagine moving his index, imagine moving his digits as we monitored his brain activity. And lo and behold, the sensory and motor parts of the brain that are involved in the hand lit up.
Middle. Ring. Index.
There are challenges. Eventually, the brain builds scar tissue at the implants, limiting the motor electrodes. But one patient's implants have lasted 8 years and counting. Scott Embry's have been working more than 2 years.
You have been a subject of this work for years now.
Yes, sir.
And I wonder why.
I wanted to have someone else have the opportunity to become independent again.
The most meaningful work of your life.
Yes, sir. 100%.
The greatest independence might be no prosthetic at all. And we saw this astounding possibility with a pioneer, Austin Beggin. His brain impulses are rooted not to a robot, but to implants in his own arm that fire his muscles. What function did you have in this hand before the implants?
Oh, absolutely none.
Nothing. You couldn't move it at all.
Nah, so the only thing I can do really is shrug my shoulders and kind of shift them. Unfortunately, that was all that came back after my accident.
His accident was on a vacation celebrating his college graduation. Diving into a submerged sandbar left him quadriplegic. Now, motor and sensory impulses flow through the ports in Begin's skull and a computer, bypassing his damaged spine.
Relax, close.
The research is led by Bolu Ajiboye, a biomedical engineer at Case Western Reserve University.
Our goal is to restore complete functionality of the upper arm, including dexterous hand function and the ability to reach out, so that Austin and others who have suffered severe spinal cord injury can regain some level of functional independence.
Bring my arm forward.
The cradle under his arm only supports the weight. All of the motion is his own. It takes effort. He has to concentrate.
A little bit quicker. Open hand, relax hand, close hand, relax hand, open hand, relax hand.
And the computer needs frequent adjustment.
How'd that feel?
Good?
Good.
But his parents, Shelley and Brad, showed us where this could lead.
Carrot, or would you like to have a nice granola bar?
I'll take the granola bar.
Yeah, I figured.
Beggin retained limited feeling after his injury, which makes him ideal for evaluating the artificial sense of touch.
Pointer finger. So if I can extend first.
His motor skills,
let me open my hand for you.
Continue to grow.
And squeeze around it. You'll feel me really start to dig in right there.
You got a grip.
Yeah, it really is. And let go, yeah. And I'll bring the arm back up.
Congratulations.
Yeah, thank you. Thank you so much.
Amazing advances are coming quickly. Danny Werner lost his foot in Vietnam.
It's on. But 47 years later, he was reconnected to touch in an artificial foot.
Can you feel that on your toes?
Yep. Which helps him balance, climb stairs, and walk on uneven ground. Brandon Prestwood's next device will replace some wiring with Bluetooth connections.
Especially the thumb. Thumb's spot on.
The cost of his experimental rig and surgery is estimated at roughly $200,000. But an eventual commercial system may cost significantly less, while delivering moments that are priceless.
What did that mean to you, to feel Amy's hand in yours?
The world. I was a whole person again. I didn't have to worry about those dark thoughts creeping back in.
It's just giving me back my husband, who means the world to me. He's his self again.
Himself, because the feeling of feeling is so much of what makes us human. Maybe that's why, when we see a tender moment, it is said to be touching.
I love you.
In a decade of war, more than 1,300 Americans have lost limbs on the battlefield. And that fact led the Department of Defense to start a crash program to help veterans and civilians by creating an artificial arm and hand that are amazingly human. But that's not the breakthrough. We don't use that word very often because it's overused, but when you see how they have connected this robotic limb to a human brain, you'll understand why we made the exception. As we reported last December, to take this ultimate step, they had to find a person willing to have brain surgery to explore new frontiers of what it is to be human. That person would have to be an explorer with a desperate need, remarkable courage, and maybe most of all, a mind that is game.
The person they chose is Jan Sherman, a Pittsburgh mother of two and writer with a mind nimble enough to match wits on The Wheel of Fortune in 1995.
I'm going to solve the puzzle. Go ahead. 2 cute for words. Yes.
When her mind triumphed, her brain sent signals of delight to every muscle in her body. But a year after this moment, those brain signals were being cut off.
One day I had trouble. In the evening, I was making a lot of trips in and out of the car. It felt like my legs were dragging behind me.
Within 2 years, a genetic disease called spinocerebellar degeneration broke the connection between brain and body. Now at age 53, Jan Sherman can move only the muscles in her face and a few in her neck. She's dependent on a caregiver for nearly all of her daily needs.
52 across.
And her mother, to help her solve the puzzles she loves.
Healed? Oh, you're good.
At the same time Jan Sherman was putting her mind to a new life, a neuroscientist just across town at the University of Pittsburgh was imagining how people like Jan might be restored. Andy Schwartz, on the right, is working on an ambitious Defense Department project called Revolutionizing Prosthetics. 5 years ago, we visited his lab, and Schwartz showed us how he implanted tiny sensors like this one into the brains of monkeys, and then wired them to a crude robotic arm. Schwartz told us that when the monkey thinks about moving his own arm, his brain cells or neurons fire off electrical signals. The sensor in his brain can pick up these signals and send them to the robot.
So he's operating the arm in 3 dimensions, up, down, forward, and back. As well as the gripper. Well, what you're telling me is that the monkey is operating this arm with nothing but his thoughts.
Absolutely.
What are the chances that a human being would be able to do the same thing?
Oh, we think a human being could do much better.
That conversation was in 2008, and since then, the $150 million Revolutionizing Prosthetics program has reached farther than most thought possible.
Awesome.
Dr. Jeffrey Ling, a retired Army colonel and neurologist, is in charge. After seeing the wounded on several tours in Iraq and Afghanistan, he told his team that he wanted a breakthrough within 5 years.
Did any of them say, look, Colonel, we're not sure we can do this?
Oh, absolutely. They thought that we were crazy. But that's quite all right, because I think it's in our insanity that things happen.
That madness led to genius in labs all across the country. At the Applied Physics Laboratory at Johns Hopkins University in Maryland, Michael McLaughlin led the multi-million-dollar engineering of what has become the most sophisticated hand and arm ever developed. It's the same size and weight of an average man's arm and hand. And everything is inside, including the computers and the batteries.
Is there anything that your natural arm and hand can do that the mechanical hand can't?
Well, I can do this.
Okay, there's that.
But other than that, virtually everything your natural hand can do, this prosthetic is able to do. Same strength, too.
Same strength?
Same strength. So we can curl 45 to 50 pounds with the arm.
They've thought of a lot of ways to use it. When set on wheels, it can bring a human touch where no human can go. In this demonstration, we wore a visor that showed us the video feed from the robot. These gloves moved the robotic hands, and we practiced pulling a wire out of a bomb.
Come on, give me that pinch.
There you go. Awesome.
But the holy grail in the project was finding a way to connect the robot directly to the brain.
Who wouldn't want to do this? When they told me, I heard about the study, I said, oh, absolutely. I couldn't not do this.
In 2012, Jan Sherman put herself on the line for a more sophisticated version of the surgery they had done earlier in the monkeys.
There's a brain surgery involved. It's experimental. Why were you so excited about it?
I've always believed there's a purpose to my illness. I didn't think I would ever find out what it was in my lifetime. And here came this study where they needed me. You know, they couldn't just pick any Tom, Dick, or Harry off the street. And in a few years, the quadriplegics and the amputees, it's just going to help. The Department of Defense is funding some of it for the vets. To be of use to them and service to them, what an honor.
What I'm going to do right now is I'm just making some marks here in your hair.
The procedure was done by University of Pittsburgh neurosurgeon Elizabeth Tyler Kabara, who showed us that the area that controls hand and arm movement is accessible right on the surface of the brain.
What are the dangers?
We worry about if we were to accidentally tear a blood vessel while we were putting them in, that we could cause a blood clot that would collect on the surface of the brain. Probably the thing we worry about the most is the possibility of infection.
I mean, you do have a connection through the skull to the outside world.
Absolutely.
May I have some irrigation?
During the 6-hour surgery, 2 sensor arrays, each the size of a pea, were placed on the surface of Jan's brain.
Woohoo!
Then they were wired to 2 computer connections called pedestals, the gateways to Jan's thoughts.
You know, people are going to look at those pedestals in your skull and they're going to think, that has to hurt. Is it painful? Has it been difficult in any way?
For a few hours after I woke up, I had the worst case of buyer's remorse. I was thinking, oh my God, I had brain surgery. Why didn't anyone stop me? Why didn't they say, Jan, you're crazy? But as soon as the headache went away, that kind of talk went away too.
5 months after the surgery, we came back to see whether she would be able to control the robotic arm with nothing but her thoughts. They plugged her brain into the computer, and this is what we saw.
I can move it up and straight down and left and right and diagonally. I can close it and open it, and I can go forward and back.
That is just the most astounding thing I've ever seen. Can we shake hands?
Sure.
No, really.
Yeah.
Like, come right over here?
Yes, you come over
okay.
there. And grasp your hand there. There we go.
Oh my goodness. Wow.
And I can do a fist bump if you'd like.
That's amazing. What are you doing, Jan? What's going on in your mind as you're moving this arm around? What are you thinking?
Okay, the best way to explain it is raise your arm.
Uh-huh.
Now,
Right.
what did you think about when you did that?
Well, not very much. I do it all the
Exactly,
time.
it's automatic.
Is that hard work? Are you having to concentrate?
No, it was hard work getting there. I struggled greatly to go up and down at the beginning. Now up and down is so easy, I don't even think about it. Side to side, don't even think about it.
Just like
that.
Your arms used to.
Yes.
We asked Dr. Ling, the program manager, where all of this is headed.
I'm old enough to have watched Neil Armstrong take that step on the moon, and to watch Jan do that, I had the same tingles, because I realized that we have now stepped over a great threshold into what is possible. And very importantly, what patients can now expect in terms of restoration. This is very important part, not rehab, but restoration of function.
I wonder what your experience with Jan has taught you about the brain and the brain's ability to adapt to new circumstances.
I think it's taught me something really fundamental, and that is we are tool users, and our arms and our legs are just tools for our brain. And so when we give another tool, in Jan's case, a robot arm, she will adapt to that tool to do the things that she wants to do.
Of course, many who could use a robot arm are not paralyzed like Jan. They're amputees, and for them, the project has found a way to connect the arm without brain surgery. 58-year-old Johnny Mathney lost his arm to cancer. Dr. Albert Chi from Johns Hopkins Hospital found nerves that used to go to Johnny's hand and move them to muscles in his remaining limb.
Now, elbow extension.
Sensors on his skin pick up the brain signals from the nerves and use those signals to control the robotic arm.
Come here, I want to see you.
So even though the limb is missing, the brain still sends the signals as if the limb was still there.
Correct.
Johnny, it feels in your mind like your hand is there again?
Yes.
As if your arm had never been lost.
Correct.
Unlike Jan, the connection for Johnny runs both ways. Sensors in the fingers send signals back so he can feel what he's touching.
Okay, I'm holding the object, and you can close on it.
To see how well, we put him to the test.
Hard or soft?
Soft.
Correct. Very good. Now let's try again. I'm holding the object. Hard or soft?
Soft.
Yep, quite right. All right.
He got it right every time.
Hard or soft?
Hard.
Amazing.
The next person to have Jan's surgery will have additional sensors placed in the brain to receive the sensation of touch. Andy Schwartz believes that will help with some of the things that Jan has trouble with.
Okay.
For example, sometimes when she looks right at an object, she can't grab it.
Okay, I'm going to take the cone away. Just go ahead and close it.
Oh, sure.
So as soon as I take the cone away, there's no problem. But as soon as I put the cone there, she can't do it.
Why is still a mystery. The progress is coming rapidly. They're working on a wireless version of the implant to eliminate the connection in the skull. And Dr. Jeffrey Ling told us that the lab experiments will one day enter the real world.
We're going to not stop at just arms and hands. I think that it's going to open the way for things like sight and sound. And my dream that we'll be able to take this into all sorts of patients with stroke, patients with cerebral palsy, and the elderly.
I think when other quadriplegics see what I'm doing with the arm, they're all going to say, oh, wow, I wish I could do that.
That's the way I like to get cookies. Awesome, thank you so much.
I just feel very honored to be the one who gets to do it.
When Americans are wounded in Afghanistan or Iraq, no expense is spared to save their lives. But once they're home, if they've suffered an amputation of their arm, they usually end up wearing an artificial limb that hasn't changed much since World War II. In all the wonders of modern medicine, building a robotic arm with a fully functioning hand has not been remotely possible. But that's starting to change. You're about to see a remarkable leap in technology called the DEKA Arm, and it's just one of the breakthroughs in a $100 million Pentagon program called Revolutionizing Prosthetics. To see how far they've come, have a look at where they started.
It's a basic hook, and I can rotate the hook like this and lock it.
Fred Downs has been wearing the standard prosthetic arm since 1968, after he stepped on a landmine in Vietnam.
In those days, they didn't have a lot of sophistication about it. It's just they'd fit you and say, this is your arm, this is your leg, and it was the best technology available in those days, and you just had to make yourself learn how to use it, and I did.
Today, Downs is the head of prosthetics for the Veterans Administration.
This technology has not changed since 1968 or even before.
It was before. Actually, this arm was basically developed World War II era, after the war.
There's a hook, something out of Peter Pan, and that is just unacceptable.
Dr. Jeffrey Ling is an Army colonel and neurologist who's leading the Revolutionizing Prosthetics program. He's a physician with big dreams and little patience, especially when touring Walter Reed Army Medical Center and meeting the troops he's working for.
We in the military have a saying, leave no one behind, and we're very serious about that. And that doesn't mean just on the battlefield, but also back at home.
Ling told us they've made great strides in artificial legs, but a good arm has never been within their grasp.
If you look at your hand, it's an incredibly complex piece of machine. What nature has provided us is extraordinary. The opposable thumb, the 5-finger, independently moving, articulated fingers. It's fantastic what this does.
And when you lose your hand, you've lost something that makes you human.
You're so right, Scott, because think about what makes us separate from every other animal species. We have an opposable thumb. That is, in fact, what makes us human.
Colonel Ling is determined to give that humanity back. His project is run out of DARPA, the Defense Advanced Research Projects Agency, the same group that oversaw the creation of night vision, stealth aircraft, and GPS.
Give me a sense of the scale of this project.
It's a very large scale. It is very much like a Manhattan Project at that scope. It is over $100 million investment now. It involves well over 300 scientists, that is engineers, neuroscientists, psychologists.
One of the scientists Ling asked to join the team is Dean Kamen, a sort of rock star in the world of inventors who flies his own jet.
It's the fastest non-military airplane you can buy right now anywhere in the world.
His creations include dozens of medical devices and the Segway.
It's very intuitive.
Inventions which have made him a multimillionaire.
When the folks from the Defense Department came to this office and said, here's what we need, what did they tell you?
We want these kids to have something put back on them that will essentially allow one of these kids to pick up a raisin or a grape off a table. Know the difference without looking at it. That is an extraordinary goal.
He basically said, you're crazy. That's what he told us. He said flat out. He himself, who's a crazy guy himself. I mean, he is a very innovative thinker. He's a brilliant man, totally brilliant man, but mad scientist.
I thought they were unbelievably optimistic in their expectations, and I told him that.
He said to us, he said, I can do, Mark, you're crazy, but we're willing to rise to the challenge because it's important.
These are multi-axis machining centers.
Kamen took us behind the scenes at DEKA, his company in New Hampshire, to show us how inspiration becomes invention.
An engineer designs a part on a computer, he fires it up here on our network.
Kamen and his team of 40 engineers spent a year working on the problem, and this is what they came up with.
When you first started this, did you sit down at your desk and look at your hand and figure out how it worked?
Well, most good engineering is some adaptation of what nature does.
It all began by creating dozens of gears, joints, and computers that mimic nature's design. But then came the hard part, meeting DARPA's demand for an arm no larger than the average human's and no heavier than 9 pounds.
This is some of the electronics that fit inside the arm. Tell me about that.
Well, this has 3 processors on it. Think of this as 3 PCs worth of computing power, and all of this just fits, it's round because it just fits in the wrist joint.
In terms of the engineering, what was the toughest piece of this?
All of it.
The prototype had 25 circuit boards and 10 motors, but it would be no good at all unless the patients were willing to accept it.
We went and started talking to the real patients and potential users down at places like Walter Reed. And immediately we were shocked to learn even just the hollow plastic shell that they wear when they're out and about sweats and it hurts and it irritates. And we came back and realized that if we build the world's best 9-pound arm, but nobody will wear it because 24 hours a day or 12 hours a day of wearing a 9-pound arm is going to be irritating and frustrating. We said, we've got a way bigger problem here.
So Kamen's team created a new way to connect the DEKA arm to the body using tiny balloons.
And you'll notice now, if I hit this button, these things are inflating, and that's a nice, gentle pressure there. But if that's displaced all over your whole shoulder, that's an enormous amount of structure.
So now the arm is gripping tight on the shoulders so you can lift something heavy.
And as soon as he's not gripping tight and heavy, one or the other might just deflate.
Ready to put it on? Okay.
Kamen asked Fred Downs, the VA official in charge of prosthetics, to take off the hook he'd been wearing for 40 years and give the new arm a try.
I'm moving this around to see how stable my stump is inside here.
The arm is controlled by flexing the shoulder and pressing buttons built into his shoes, almost as if he's typing with his toes.
Ball of the foot, outside of the foot, and then toes.
You were skeptical.
Very, very skeptical. Because I've seen lots of inventions come along in my years of being in charge of prosthetics, and so some great stuff, but in the long run it doesn't really work because your body only has so much tolerance for gadgetry.
After practicing for 10 hours, Downs showed us what he could do.
Now I use my toes to grasp this. Feeling is hard to describe. For the first time in 40 years, my left hand did this. I almost choke up saying it now. It was just, it was such an amazing feeling. I was 23 years old the last time I did that. It felt so good to move my arm again, to do things with it. Not as fast, not as this, but it worked.
You just said, move my arm
again.
Did it feel like your arm?
It did, it did. It felt like my arm. It was me. You sure I can't take this home with me, this arm? I'm ready for this arm.
If Downs is eager to have the DEKA arm, imagine what it would mean to Chuck Hildreth, who lost both arms at the age of 18 in an electrical accident.
Push the knob. Look at that.
He's been volunteering at DEKA for nearly 2 years.
Now, it seems to me that one of the issues here would be that you don't have any feeling in this hand. So the question becomes, I mean, how do you pick up an egg? How do you pick up something that you might crush? How do you know?
I have a vibrator sensor here that tells me how tightly I'm grabbing things. The more intense the grasp, the more intense the vibration is.
You know, you've set me up here with a plate of grapes, and this I've got to see, okay? So let's, how do you pick up a grape without crushing it?
Let's see.
No way.
Consider, Chuck hasn't eaten like this in nearly 30 years. Many of the innovations in robotics that make this possible are already at work in artificial legs.
These are the latest and greatest. These are the power knees. They actually have a motor inside them. They help propel me.
Josh Blyle lost his legs in 2006 to a roadside bomb in Iraq. Last year, he became the first person in the world to walk on 2 of these. They're called power knees, legs that propel themselves and talk to each other to keep a constant speed and stride.
How fast will these go?
Faster than I can control, to be honest with you. Not to a run yet, but they do have a lot of power.
Now, making a robotic arm that moves as naturally and effortlessly as these legs is the next step in revolutionizing prosthetics. Colonel Ling says the key is connecting the artificial limb straight into the nervous system.
Remember, they lost their arm, but that big bundle of nerves that came out of the spinal cord still exists in their shoulders.
So the nerves that control the arm are not necessarily lost
They're not
with
necessarily
the arm.
lost, right.
And the brain continues to send those signals to those nerves when a person imagines
moving their missing limb.
That is correct.
I'm one of over 300 engineers worldwide working on this.
Jonathan Cunnahome is uniquely qualified to figure out how to tap into those signals. He's a biomechanical engineer at Duke University who lost his arm to a roadside bomb in Iraq.
Explain to me what you're doing with your right arm and the sensors and how that relates to your new right hand.
I'm imagining performing movements with my right hand, and when I do that, I'm moving the muscles that remain here in my arm. When those muscles move, they make little electrical impulses that we can detect with these electrodes.
So imagine closing your hand for me.
So I imagine flexing my wrist, doing a key pinch.
To be clear, Jonathan is controlling this robotic hand simply by thinking about moving his own hand that no longer exists.
How much training is required to move this hand with those muscles? How long did it take you to learn how to do this?
I'm not really learning so much as the computer is. I'm doing what I imagine I'd like to do, and we've taught the computer to interpret the signals and do what it is.
So it almost feels natural to you?
It does.
After 4 years and $100 million, arms controlled by thought are still a work in progress. But in the meantime, the DEKA Arm is headed to the VA for clinical testing in the hope that it will soon become available to the nearly 200 arm amputees from Iraq and Afghanistan.
Nobody ever wants to put a price tag on making a soldier or a Marine whole again, but you're talking about $100 million.
That's right.
It's a big number.
It's a huge number, but it does a number of things. Number one is, of course, it fulfills our commitment to these fine young men and women who the issue of money compared to what they have done for the service of the nation becomes immaterial. However, this is not a classified military weapons system. This is an advancement in medical technology. And the beauty of this particular effort is that this is another gift of the American taxpayer to the entire world.